Okay, good morning, everybody. So here we are for one more session of the Matemairacorana 2, an event in honor of Hildeberto Cabral's 80th birthday. And today's session, we have two talks. So the first one is by Connor Fox from CIMAT, Mexico. And he's going to talk about projective geometry of the planar Kepler orbits. So Connor, you can start whenever you want, and please everybody turn off their cameras to improve the connection.
Okay, thanks. So thanks for the invitation to talk and this organizers for this neat event. It's been fun for me to watch the recording since normally I teach at this time. But, so the topic I chose is kind of this ongoing project I've been working on here at CIMAT with Gilboa. Can you guys see my mouse if I want to point at things?
Yes, we can see.
Yes? Okay, great. All right, so we're calling it the projective geometry of these Kepler orbits. So just start by reminding some things I think everyone here is familiar with. But so when I say the Kepler orbits, what I think of is the unparametrized trajectories of Newton's inverse square law. So in a sense, we're kind of forgetting all the dynamics or the fun, but it turns out there's still some interesting stuff. So you could think of it like, I like to say it in terms of Kepler's laws. We just forget these second two, which have to serve to specify this parametrization. That's, the special dynamics associated with this force law. And we're just considering in the plane the set of all conic sections having fixed focus at this sun or source, we can call it. And so this is what I mean by Kepler orbits, the unparametrized trajectories. And the question we ask is, what are transformations of the plane that preserve this family of curves? So, something I'll make the disclaimer here. I'm not gonna really, everything I say you should add, say local in sort of two senses, local in the sense that we're asking about transformations that need only be defined on some open set of the plane, and they take, say, the arcs, the intersection of the Kepler orbits. The image is another arc of one of these Kepler orbits. And there's also kind of local in the space of curves. The transformation may only work for some of the curves, or say an open set of the curves are a three-dimensional space in this case. So there are, say the obvious ones. We all know about rotations, and there's also scalings. And then we also have, say, reflections through lines passing through the origins, these, say, discrete ones. So there's definitely this one I think everyone knows, but yes, and well, for the name, we'll call such transformations point symmetries, or maybe Lie point symmetries, because this type of symmetry is in the work of Lie on ODEs in its origins. So, just something we've said, these Kepler orbits in the plane are a three-parameter family of curves. So if we like, we can write them in this way: alpha, beta, and gamma being the parameters, and r being the radial distance from the sun. And there's this nice picture expressing this formula. So to obtain a Kepler orbit in the z=0 plane, you orthogonally project the intersection of this right cone just with a general affine plane. Yeah. So the orthogonal projection of such a conic section is a Kepler orbit with focus at the origin. And so the first thing is this full point symmetry group is a 7-dimensional group. And well, I find it interesting that this is, I'm saying is the largest possible symmetry group for a 3-parameter family of curves. So these are the most symmetric type of family of curve. And this sort of statement that this is the largest thing is sort of, this content is sort of the work of Lee, Tress, his students, and Barton. So 3-parameter families of curves are equivalent to third-order ODEs. And so what I'm saying is Kepler orbits in terms of ODEs are equivalent to this sort of simplest ODE of vertical parabolas in the plane. So there's this is from the point of local diffeomorphisms of curves, families of curves on the plane. It's Kepler orbits are the same as this, say, it's called the flat 3-parameter family, in analogy with, curvature being 0. There are certain invariants of ODEs of third order, which they all vanish for this thing, and they all vanish for the Kepler family of curves. Okay. So I think what I'm going to talk about, there's kind of two ways we could talk about, say, this, how we know this 7-dimensional group is say complete. There's nothing else, no other symmetries than these ones I'm about to explain. But I'd rather focus today on more like, well, what you can say, use these symmetries for to make, say, some geometric properties of this family of curves, make it easier in proofs, because you're allowed to apply these symmetries and take yourself to an easy, say, general position. So here's sort of the quick sketch of how you can see this symmetry group. So first is this picture we started with. So the Kepler plane is here, the z=0 plane. And we have this right cone, x squared, y squared, z squared. So you think of z like r when you intersect with the upper half. And, well, this cone, I'm going to think of both halves as kind of like a double cover of the Kepler plane. And so since everything's local, same question is just to ask for transformations of the cone which preserve planes. So, well, take a linear action that preserves the cone. So you can scale and you can act by elements of this Lorentz rotations, right, to preserve the light cone. And the Kepler orbits are just planes. We're gonna only look at, say, non-collision orbits. So we're not considering planes passing through the origin. They're kind of like, you could think of them as like an invariant set. So the origin is always fixed by this action. So this is a 4-dimensional group. So we have a larger set of symmetries of the Kepler orbits now. And then to see the full group, you sort of enlarge one more time. You say, okay, this picture of the cone in R3 is just seeing things in an affine chart of projective space. So you think of, this is how we write a point in projective space. So we think of this as like the W equal to 1 chart, and we have this conic, well, degenerate conic, because it has a 0 in terms of W. It doesn't depend on W, but right. So it looks something like this. It's this cone here with a closed up because we've added this circle at infinity. And the Kepler orbits are still just sections by projective planes of this thing, this projectivization of the standard right cone in projective space. So now you can act by any projective transformation of space that preserves this conic And so you have the ones before, but you can also say translate shift W arbitrarily, so you get kind of a translations. And this is the 7-dimensional group that we stated in the theorem. And then by this kind of more fancy stuff of Cartan and Lee, you can show that this is the entire symmetry group. Nothing else occurs, even when you add in all these local phrases. Okay. So and here, right, here's how you write a projective plane, and because I'm going to consider d equal to 0, which is just another way to say that this sort of invariant set of say collision rays or sections by planes passing through the origin. I'm just going to focus on the say, I don't know, non-degenerate Kepler orbits. So we'll take that case. All right, so that's kind of how you see them acting in space. You know, you take some matrix here, you act on XYZW, you go into this affine chart, and then you finally, if you want to write it out on the plane, you project it down to orthogonally project setting z equal to r and taking the first two coordinates. Okay, so we found it easier when we're working with these things to look at the action on the dual space. So the space of planes in RP3, or we call it like RP3 star, or the dual projective space. It also is acted upon by, say, the transpose action of this. And so that's what I want to explain now, because you see the action a little simpler. So let me just say that, so here's what we have before, R3, here's, say, our plane. I'm going to write it with ABCs. Who's considering planes not passing through the vertex. And so in the dual space, we're going to delete this set of planes passing through the vertex, take an affine chart. So ABC are coordinates. And so a point here corresponds to a plane in R3 or in RP3. Okay, and when we're calling it R21, because there's kind of a natural null cone and Minkowski inner product here that reflects certain geometric facts. So, for instance, you know, you can think of this ABC as the direction of the normal. So, if this ABC lies in, say, this null cone in the dual space with these coordinates, it means that the plane is, say, a section by a plane. By a plane tangent to the cone shift, shift. So these blue guys are parabolic orbits, these blue ones. And then if the normal vector is, say, time-like, and so here from this point corresponding to this red plane, it's these interior of this null cone are the elliptic orbits, and the exterior are the hyperbolic orbits. Okay. And then another thing, sort of, so kind of just describing, say, landmarks in this ABC space, so you can see what, you know, when I give you certain subsets here, we can sort of see what they represent. So another thing is, you can ask about the lines, right? There's straight lines in the dual space. So if you take a null line, call it, so a line that's like a generator of this cone or any translate of it. So these blue lines here, or any kind of translate of them, we'll call these null lines. So this represents a one-parameter family of Kepler orbits. Yeah. And the meaning is that over here they all pass. There's a set of planes passing through a line tangent to this white cone, or that's to say, when you project them, you get a family of Kepler orbits that are all mutually tangent at a point. Similarly, you can take, you know, there's sort of these three classes. If you take a time-like line, for example, the c-axis, or any translate of it, you get, say, nested orbits, or, you know, disjoint. So this c-axis here would just represent, you know, rescaled circles centered at the origin. And then similarly, if you take a space-like line, something like steep, right? Let's make it like that. Right, you get these transverse orbits intersecting in 2 points. Okay, so there's the meaning of lines, and we like the dual space because if I want to act by these things, it's not there's no sort of division by W to go to the affine chart. On the dual space, it's just normal translate by an element of R21 and act by the Lorentz rotation. So it's easier to see the action here. So it's nice to kind of orient yourself with what the ABC parameters mean in terms of the conic sections. Okay. So I want to mention next, let me just stay here, some of our favorite subfamilies. So, so here's the equation we started with. Rather than alpha, beta, gamma, I write it with the A for this Runge lens vector and M for the angular momentum. So here's the standard relation. So you can use this to just, it's not just some simple algebra, to relate the A, B, and C's to families, say, with fixed energy, right? So, for example, if you, or what, you know, whatever you like, fixed major axis, fixed eccentricity. We've also found fixed minor axis to be pretty neat. So, maybe let me try to say that again. You have this relation between energy, momentum, and all of these energy momentum are like latus rectum, major axis, eccentricity squared. So you can describe subfamilies of Kepler orbits by fixing whatever you like, and then just translating it into an algebraic equation, for the A, B, and C's. Right, so you just kind of, it's just kind of a division by m squared, because the way we write it out here for the projective duality is ax plus by plus cr, right? R is like replaced by z. Okay, so some simple algebra, you can write out the surfaces corresponding to some two-parameter subfamilies. So it turns out that if you say fix the energy, you get, or major axis is the same thing. So I wrote major axis here in red. You get, here's in the dual space, you get this hyperboloid of two sheets that's tangent to the, or one of its branches is tangent to the origin. Okay, so these are the orbits of fixed energy. It's really, you kind of get both signs of the energy at the same time. So this branch down here, the one that's contained entirely in the light cone, are the negative energy guys. And the one up here are the positive energy, hyperbolic orbits. So they have the same value of energy, just flip the sign. So positive, negative. Okay, so another one in blue that I draw is the fixed orbits with fixed minor axis. So this is just the standard two-sheet hyperboloid drawn inside this null cone through the origin. So they're just translates of each other. And then, so this is what I've written out here. Well, I guess I wrote a little more. So this part here, you get the surfaces in the dual space, and then you use projective duality to say, well, the dual of a quadratic is another quadratic. Right? This is sort of the envelope of all these tangent planes. Right? This is a family of planes, so they envelop another quadratic surface in R3 with the usual, this XYZ space. So the minor axis orbits, they're dual to the usual, also the usual hyperboloid of two sheets inscribed in this now XYZ cone. And when you apply this shift, it turns out it's paraboloid inscribed in the cone. Sort of this circle here represents the guys at infinity, which in this chart d equals 0 are the planes tangent to the cone. Okay, so just by knowing that projective duality, you have this kind of nice description of orbits of fixed energy, which is also found in an article of Giventhal, that to find orbits of fixed energy, you take a plane tangent to an inscribed paraboloid, intersected with the cone and project. So that's just automatic from the definition of duality. and this sort of playing with algebra. Same thing, well, we have this new family. If you take an inscribed hyperboloid, take a tangent plane and project, you get the orbit of fixed minor axis. And so the whole kind of two-parameter family is described this way. Okay, and so, well, I'll just comment on the symmetry group. That they have this SO2-1 symmetry group. In this case, it's not like the full family of Kepler orbits that this is flat. It's sort of like the second most symmetric. So, two-parameter family of curves are second-order ODE. Sort of the flat case is like y double prime equals 0. So like lines in the plane. It has an 8-dimensional symmetry group, right, projective group. And sort of the next possible symmetry group is exactly this SO2-1. So there's kind of a gap. It goes from 8 to 3. Just like with surfaces, Riemannian surfaces, it goes from 3 to 1. You kind of have geodesics on the sphere, and then the next most symmetric is geodesics on the surface of revolution. Okay, but well, and there's kind of these surprising transformations that you see. So this is a map of the plane to the plane corresponding, represented by just this translation up or down of the hyperboloid of two sheets. So if you write that out in coordinates, this map sends, if you take the image of a ellipse of fixed minor axis, you get an ellipse of fixed energy, fixed major axis. So, okay, so the next, how much do we have till 9:10, or how much time was there?
It's about 3 minutes.
Oh, okay. Well, sorry, it didn't. Okay, so let me now talk about fireworks. So we're used to this thing with, in the constant gravity minus g, orbits are vertical parabolas, and they envelop another vertical parabola. If you take the one-parameter family of parabolas emanating from a point with fixed energy. Okay, and a similar thing you can see in this picture. So first you see it for orbits of fixed minor axis. If you fix a point in the Kepler plane and you take all the orbits of Kepler orbits of fixed minor axis passing through this point, it's a one-parameter family, and they envelop a Kepler parabola, right? A parabola with focus at the origin. And similarly, if you take ellipses of fixed energy passing through a fixed point, you envelop another Kepler ellipse. So I guess I'll just finish by telling you the proof or construction of this. So here I'm drawing the picture in the dual space. So here my blue curve is this hyperboloid of two sheets, one of the branches for the fixed minor axis, and the fixed point is dual to a plane in the dual space, in the R21. So here's my plane. This intersection here are all the orbits of fixed minor axis passing through a fixed point. And you want to find some other point, well, you'd hope, right, that they envelop some other curve of the family still. So I'm calling it epsilon here, and this is what it is. But what you'd like by this property of if two Kepler orbits in this R21 are connected by a null vector, that they're mutually tangent. So you want some point so that if you connect it to any of these green guys, beta is connected by a null vector, right? Or this is this condition in terms of the inner product, that this vector beta minus epsilon is a null vector. This means that epsilon is tangent to every curve of this family. So you just play with some projective constructions. I mean, so you have this plane, and you can always take its polar, which is the intersection of all the tangent planes to this green curve. It turns out, right, that for quadratics, these always intersect in a point called this pi perp. Okay, so it's defined by the property that I'm writing everything with Lorentz in a product. This is the property defining pi perp for every beta in this intersection. There, it turns out there's 1 point here. Okay, and it turns out that also, okay, because pi is dual to a point on the cone, its perp is a null vector. Okay, and then well, it turns out pi perp is not this point that's the envelope, but half of it is. So this is just this property that we wanted the envelope to have. So if you rescale it by 2 and expand here, you get exactly 0, a cancellation. Okay, so this is the envelope. So to construct it, you take this plane, you intersect all the tangent planes through this curve of intersection. You get the point pi perp, which is always a null on the null cone, and then you rescale it by a half. And this point here is the envelope of this family of curves. So this was sort of an easy. It's kind of it's a pretty easy calculation using the Minkowski geometry. And well, okay, the claim that it's a parabolic orbit for fixed minor axis is just that, well, we saw that the parabolic orbits are the points that lie on this null cone. Okay, and then, well, this construction really doesn't actually depend on the choice of origin that we use in the dual space. So you can do it, just translate up and down for the orbits of fixed energy, and that's how you get that. If I take, say, a negative energy guy, its null cone is sort of, it's just this whole shifted picture. The point on the null cone, that's kind of this envelope of some intersection, is also an orbit of negative energy. It stays inside the light cone. Okay. Well, I think I went a little slower than I imagined, but well, I'll just say there are lots of other fun constructions you can do in a similar way. So we found there's this other nice kind of surprising property that if you think of the Kepler orbits as curves in RP2, and then you take the curves in the dual plane in these specialized charts, they're dual to circles. So the theorem of osculating circles translates to a four-vertex theorem on osculating Kepler conics, which is kind of neat. And well, that's what I wanted to finish with. So well, thanks for your attention. Muito obrigado.
Okay. Are there questions for the speaker?
Maybe just a comment?
Yeah.
Sure.
I want to mention that I published a picture which is not in your talk. This is in my paper, the projective dynamics and classical gravitation in this various cylinder. And the group, I fixed the angular momentum. So instead of having a 7-dimensional group from Kepler ellipses to Kepler ellipse, I have a 6-dimensional group, and this group is just some linear transformation which preserve a cylinder, vertical cylinder. I don't know if you met this one also.
I'm not sure the cylinder, but we did think about fixed angular momentum here. Oh, and well, maybe there's some. We found that it has so they represent intersections with fixed planes passing through a fixed point, or like in these coordinates, say just a flat plane, c equal constant. So maybe it's some different choice of coordinates. We saw it as a flat plane, but you're including the orbits at the orbits
just mention
origin.
Yeah. This cylinder was then useful in the two fixed center problem. I mean, it was very convenient to project two fixed center problem to another one and on the sphere.
Okay. Yeah. It's also interesting these curved Kepler problems too. Well, lots of things from central projection are sort of the same because we forgot all the parameterization. So,
yes.
For instance, these, I didn't say it, but these hyperboloids of two sheets, so we have kind of these special ones I said, sort of this centered at the origin and then translated down so it's tangent at the origin. But all these intermediate ones are like Kepler orbits on a sphere of fixed energy, right? They're centrally project to curves in the plane, and they're kind of also they're all kind of the same if you're just looking at them from the point of diffeomorphisms of the plane. I think there's lots of neat other families of curves you could try to use these symmetries for to say something geometric about the family. Thanks.
Okay, thank you. Other comments or questions? Connor, you mentioned in the abstract of your talk some applications. I don't know if maybe you didn't have time to talk about that. Do you want to mention one of them?
Sure. Maybe like by application, I mean, we get kind of new proofs of known things, or so for example, this fireworks thing. I guess by application, I just mean, proving things about the geometry. Another application that we had was this kind of, I think it's kind of neat that we forget time at the start, but you find, say, a special Lambert theorem for fixed minor axis orbits, which I think is Lambert theorem is usually pretty useful. And this one is kind of funny because so it says if you fix the minor axis and the chord length between 2 points on this orbit of fixed minor axis and the difference of the distances to the sun, you can determine the increment in eccentric anomaly. It's kind of, usually the usual Lambert theorem is major axis, the sum of the distances to the sun and time. But you see these things in the Minkowski geometry for minor axis, they kind of pop up naturally. The eccentric anomaly is sort of like the arc length along the cone, say here, and it's preserved by SO21. So you have kind of an easy way to get invariance with this family of fixed minor axis. So that's kind of what I had in mind with the applications, just new ways to get things about these fireworks or this Lambert theorem or this kind of special four-vertex theorem. So applications of this set of symmetries to make it easier to prove kind of, I don't know, to me they're kind of hard to see geometric facts, or that someone tells you that the set of all ellipses in the plane with fixed major axis is equivalent, under some map of the plane to all orbits with fixed minor axis. It's hard to see, but once you just see this translation, it's like nothing. So that's what I had in mind when I said applications.
All right. Okay, thank you very much. So I guess we can close the talk, right, Annette, because we are on time for the second talk. All right. Thank you very much, Connor, once again. Okay. So moving on to the next talk, our speaker now is Marcelo Marquezin, from Universidade Federal de Minas Gerais, Brazil. He's going to speak about the family of linearly stable equilibria in the Sun-Earth sail problem.
Thank you.
Turn off our cameras.
Can you see my? Can you hear me?
Yes.
Okay, and can you see the screen?
Yes.
Okay. All right.
We cannot see your talk, your presentation.
No?
No.
So wait. Wait.
You shared full screen.
Did I?
Yeah.
Okay, again. And now?
No. Oh, it's coming. Yes.
Yes?
Yes.
Can I start then?
Go ahead.
Okay. I'd like to thank the organizers of this meeting for the opportunity to be able to be here and see old friends and talk a little bit about my recent work with Professor Tadashi Yokoyama, and especially for being able to participate in this reunion for the celebration of the birthday of our dear friend Hildeberto. Thank you very much. I will ask for excuse because I try to keep my talk very introductory, because I have invited several students of mine to participate, and so I'll try to do a general talk and everybody can follow. Okay, let's go then. Maybe I should talk a little bit about the motivation. The motivation for this is that there have been proposed some missions to study the let's say the dark side of the sun, the side which is always hidden from us, and so missions to the Lagrangian L3 point have been proposed, but the problem with them is that they are really behind the sun, and the communication or a satellite or a probe from that point to Earth would be impossible. So the idea here is to put some kind of sail in the probe, the satellite, and with this to shift a little bit the L3 point, raising it up or moving it sideways in such a way as to permit the direct communication with Earth. All right, and then we could study the sun's magnetosphere, solar winds, the evolution of the sunspots, and the solar ejection of coronal mass, which is very important nowadays. If you could predict it with several weeks of advance, it could avoid some problems with our system of communication on Earth, and that would be very important because nowadays the whole world is very dependent on the global communication. So that's the motivation. So I have two binaries. One of them is luminous, and it's called a star. The other one is called a planet, and a third body with mass much smaller than the mass of the binaries, which is the infinitesimal body, a solar sail. So it's we consider a circular motion. The planet rotates in a perfect circular around the star, which is fixed on the origin, and we suppose the planet is on the positive x-axis, and the system rotates with an angular velocity omega. Okay, we call the vertical axis h, and y completes the coordinate system. Well, we shall study the particular case of Earth and Sun, And so we introduce here the constant of gravitation and what we call the parameters. Parameters for the planet, mu e, and the parameter for the star, mu s. Also, we consider the angular velocity vector, omega. The planet is at the position RE00. So the distance from the central star, the distance to the origin, is the RE, capital RE. The Sail position, that's the important thing here, is XYH, and its distance from the star is obviously this given by the square root of the sum of the squares of the coordinates. And here you have the important new thing, that is the Sail acceleration vector, which is due to the stellar radiation, and call it AS, with coordinates A1, A2, and A3, okay? And we also have another vector that is the Sail position in relation to the planet, that's RE, okay? So the Sail distance from the planet is this one given here below. All right, here we have, I borrowed this picture from the work of Allan Kardec, Bertacchini, Tadashi, and Sanchez, and just is basically what we're talking about, except that the vertical axis is h, and I'm not going to use this sub-indices e under the axis here, under the gamma, okay? But mainly it is this, the star, the Earth, and L3 is here. So when we include the Sail, it is shifted and can be shifted in many directions. We are going to study the possibilities and the stability of this equilibrium. Here I have, just to give an idea, this is the Icarus Sail, the Japanese solar sail. There's another picture of it here, more interesting, just to show that in fact people are doing the problem is real. Some space missions are being done taking in consideration solar sails. Okay, so the equation of motion for the sail is given by this equation 1, all right, where we have the the equations for the rotating system, and the second on the right hand side here, mainly we have the acceleration due to the radiation pressure. Okay. Okay, so we're gonna rewrite. Okay, all right. Let me talk about this. The acceleration. The acceleration vector depends on the reflectivity properties of the sail, mainly given by the lightness number beta, and the reflective coefficient, which is ρs. Ρs equals 1 means that the sail is perfectly reflecting, while ρs equals 0 means it's a stellar panel, which absorbs all the photons produced by the sun. And we normalize it so that the sum of both is equal to 1. We are going to consider here a perfect reflecting sail, so ρs will be equals to 1 for us. Also, we have the stellar sail orientation is given by two angles. We're going to talk about them in a second. They are called the con angle and the clock angle, which is given here by gamma and delta respectively. Okay, so here I rewrite the equation of motions in the coordinates, and I present the potential function capital omega, given down here. And well, as we are going to study the equilibrium, right? So we're going to consider the equations in which the left-hand side of all these three equations are equal to 0. All right. But in order to do this, we have to figure out the expressions for the acceleration, A1, A2, and A3. So we do this now. For a sail with area A, the force due to the reflected photons is given by this formula here, Fr, and the force gives due to the absorption is given by this formula here. So you get that the acceleration, solar acceleration, is given by this formula down here. And as I said before, we're going to consider ρs equals to 1. So the second term here disappears. And we are left over, oops, well, not yet, but we are left over only with this first part. Okay. I introduce here the vector normal to the sail surface, and P, given by this expression, is the stellar radiation pressure at a distance r from the star. We consider here a parameter r naught, which is the distance from the planet to the star, just to keep this normalized and keep this a little bit simpler. So here's what I mentioned before. We shall consider perfect reflecting sail. And so the acceleration due to the solar radiation is given by this equation 3. And we have where we have this normal vector n here. So we have to figure out how to write this normal vector n. Well, just a comment here. We notice that the stellar radiation pressure is proportional to the inverse of the square of the distance. So it's common to write 2πa over ms, the mass of the sail, as a correction to the star's gravitational attraction, through this equation down here. And we can consider, we can isolate beta here and get an expression for it. And in doing this, the stellar sail acceleration may be written in terms of the stellar gravitation as in the equation 4. Okay? But the parameter beta, it can also be okay, this what's written here is what I just said, right? But the parameter beta, it can also be determined in another way, and McInnes does it. And this is an expression for beta in terms of sigma star, which is given by this expression here. Big L is the luminosity of the star, c is the speed of light, m is the mass of the star, g is the gravitational constant. The sigma without the star is the mass to area ratio of the sail. It's a very important parameter because you're going to see that the stars to be effective, or either they have to have, the sail to be effective, they have to have a small sigma parameter, either a very small mass or a very large area. This is one of the problems to deal with the sails. Okay. Well, just an observation based on what I said. When the mass per unit of area ratio equals to the critical stellar sail loading parameter, that's the sigma star that I just mentioned, we have that beta is equal to 1, and the star radiation pressure and acceleration and the star gravitational acceleration balance each other. They're exactly the same. Okay, now we follow the notation of McInnes in his book, and we introduce a system of reference centered on the sail. So we consider r hat as the unitary vector in the sun's sail direction, as it's mentioned here, and p and q given by these expressions forming the orthonormal system centered on the sail. We have a better drawing here, borrowed from the work of Ariadna, Janet Hiller, and Narcis Miguel. The sun is here, so the sun sail direction RS is horizontal here. We have the normal vector to the sail, and we have the Q and P given by these expressions, forming an orthonormal system of reference. This angle here, we shall use in our work, we shall call it gamma and not alpha. Okay, so I made this observation here. And this is the other angle that's important in the orientation of the sail. That's delta. Delta is delta. We keep the delta notation. But this angle here would be where you see alpha here, read gamma. All right, so we have to find out the expression for the normal vector in this new system of coordinates. And it ends up after some computations that the normal vector is given by this expression in the system RPQ, where I've just mentioned the angles gamma and delta are the ones shown in the picture. Delta is called the clocked angle, and gamma is called the pitch angle, also the cone angle. The gamma corresponds to the nutation, and the clock angle corresponds to the precession angle. Okay, so finally you get this weird expressions about the coordinates of the normal vectors. And the equation of motions, after all this, is written in this cumbersome expression 6. All right, where we have introduced the big omega tilde given by this expression below here. So we want now to find the equilibria for this problem. So you want to solve equations. Oh, sorry, there's observation here. What's this? Oh, okay. We want to study the equilibria, and we want to study equilibria in two cases. We firstly found more interesting to try to determine the Hamiltonian case. The Hamiltonian case is when gamma is equal to 0, so that the vector position, the normal vector, is parallel to the vector position of the cell. This means gamma equals to 0. We are not going to study the case where gamma is equal to plus or minus pi over 2, because this represents that the cell is the sail is parallel to the direction of sun sail, and therefore the influence of the solar pressure is null in this case. So we consider gamma always in this work. We consider gamma not equal to plus or minus pi over 2, and we start studying now the Hamiltonian case, which is gamma equals to 0. So when gamma equals to 0, the equations of motion are still this, but they become a little bit simpler because gamma is equal to 0. We introduce, like Wintner did many years ago, introduce new variables. So we are able to write the Hamiltonian for the expression. And the Hamiltonian has many interesting properties. We are not going to deal with the properties of this Hamiltonian systems here, but the equations of motion become very nice in terms of the Hamiltonian function. And here we introduce the particular case of the sun, our sun, Earth, and the sail with the numbers, the parameters corresponding to the real solar system. We come back to the equation of motion, and now we write here just one step back. We move one step back and write here the equations of equilibrium in the general case. I mean, Hamiltonian or not. It's kind of very complicated. We're going to deal with it in the following. But just to show that what happens when we study Hamiltonian case is that the things become a little bit simpler, because this gamma is equal to 0, and so this sine of gamma simplifies the thing. There's a cosine of gamma here also is equal to 1, the things become simpler and you get these expressions in here. So I want to analyze the equations 4, 5, and 6. Okay, we observe that, let's see here. The first observation is that in the Hamiltonian case, we cannot have equilibrium when x equal to 0. Because if x equals to 0, equation 4 here means that 0, 0, and 0 here. So we would have the expression VE times RE equals to 0, and that's not possible. Okay? Also, when if we have x different from 0, but y equals to 0, sorry, the second expression here, there cannot be an equilibrium when x is different to 0 and y is different to 0 too. Because if y is different to 0, in this expression here, you can cancel y and everything and substitute the expression back in equation 4. And again, you get an incongruence with an expression that cannot be 0. So you have this impossibility. This is the Hamiltonian case, just remember this. Another thing is, okay, so we are left with the case in which x is different from 0 and y is equal to 0. In such case, when y is equal to 0, equation 5 is trivially satisfied. Here, equation 5 is y, so it's trivially satisfied. And we have two cases to consider. The case where h is different from 0, then equation 6 above implies this relation here. And from this relation, we can take an expression for x. And from this expression from x, we can take an expression for h of x, which gives us solutions, which are the equilibria in this case. We're going to see it in more detail in lemma 1. But the second case is when, h is equal to 0. And when h is equal to 0, equation 6 is also trivially satisfied. And then again, equation 4 features as another expression for x. And this expression will then give that the point for this x, y equals 0, h equals 0, we have another equilibrium. Okay? So this reasoning justifies that we consider only the case y equals to 0. X is different from 0, so as we want to study the problem in which the sail is behind the sun in relation to Earth, we consider x negative, and h could be either positive or negative, and there's no difference in considering either one of the cases, so we consider for simplicity the case h bigger than 0. Okay, the lemma 1 is the one I just mentioned before. So we are the Hamiltonian case, and there is a limit for the values of x. I call this value x0. So if x is in this range from minus, well, this big number here, 449, 163 point something, and 0, we have necessary and sufficient conditions for the point P given by y equals 0, this x chosen in this range, and h given by this expression below here, to be an equilibrium. The necessary and sufficient condition is that the beta, the sail parameter, satisfies this relation in here. And of course, as I have said, h is given by this expression. We observe here that two things, right? First, the radius of the sun is almost 700,000 kilometers, right? So these values for x given by this lemma are smaller than the radius of the sun. So we would be in a position not perfect to analyzing, we will not be exactly behind the sun. Another thing to observe is the height given by this expression when x goes to 0, mean that when x tends to the origin, the expression from h tends to infinity. So this means that cannot be an equilibrium exactly over the north pole of the sun, but we can get high enough. We can get equilibrium position high enough in order to permit direct communication with Earth. Just choosing the value of x close to 0. Okay, we repeat the above analysis now for the non-Hamiltonian case. Excuse me. So now gamma is different from 0, and we studied several cases. We studied the cases that we consider more important to us. So the first case is h is equal to 0, meaning that where the sail is in the ecliptic plane, the plane of movement. And from the equations of movement, we can see down here, this implies, if you look on the third equation and h equals to 0, this implies, since gamma is not 0 anymore, that delta must be pi over 2, okay? And then we study two subcases. The first one is when x equals to 0, meaning that we are on the y-axis. Y is the axis which is perpendicular to the axis that connects the sun to the earth, right? When this happens, we have this equation to be satisfied, these two equations. And the result we have is that for y taken into the region given by rs. Rs is the radius of the sun. So we want y to be bigger than the radius of the sun, so it's possible for the sail to be physically located in this point. So if y is in this interval from the radius of the sun to this maximum value of y, and we consider the θ1, the angle which the tangent is given by y over, remember, big R sub E is the location of the Earth, of the planet. So it's the distance from the planet to the sun. If you consider this angle here, we can, given a value of y in this range, we can find a value for gamma and a value for beta depending on this θ1. And again, θ1 depends of y, for which we find a family of equilibrium. This is the conclusion. Well, what I just said is just written here. Okay, so we have a family of equilibria given in this non-Hamiltonian case. Remember, we are considering here the first case that x is equal to 0. Now we look for the second case when when now h is equal to 0. So which means that we're just considered the case h is equal to 0, right? Sorry, let me come back here because I made some confusion. Yes, we are in case 1, h is equal to 0. Okay, the first case studies x equal to 0, but still h equals to 0, and now we consider yet h equals to 0, but now x different from 0. This implies if x is different to 0, the equations also implies that y is different from 0, and the equations to be satisfied for us to find the equilibria are these two equations in here, and the result we have is, consider now the angle theta given by minus y over x, we have two expressions. So if we choose y and x, let me see, in a certain region, then this angle theta can be computed, and with the angle theta, it can compute gamma and beta with the expressions, and this features as another family of equilibria. Okay? The region for the range of possibilities for y and x are this one, x negative and y positive at will. Okay, yet another observation is that given x negative, any x negative, I can choose y, say high enough, in a way that I can assure that direct communication with Earth can be obtained. Okay, I have the two parameters here, free, x and y, and so with some trigonometry simple calculations, I can choose y big enough in order to permit to allow direct communication with Earth. Okay, the second case is when y equals to 0. So the sail is on the x-age plane. And now when y equals to 0, the second equation implies that delta equals to 0. And the algebraic system to be solved in order to find the equilibria is given by equation 29, where this big delta is given by this equation here. Parameter of the Earth, parameter of the Sun, over the corresponding cubic distance from Earth and Sun to the sail. So I have to solve this equation now. And again, I have freedom in x and h. I can choose at will, and through this expression 32, gamma and beta can be determined in a way that I can find a family of solutions for our problem. Here, okay, unlike the alpha used in the first picture back there in the beginning of this talk, alpha here for me means this expression is the angle which sine of alpha is h over the distance from the Earth to the Sun, to the star. Okay, once we found a family of equilibria, we now want to know if they are stable or not. So we're going to analyze the linear stability in both cases. We start with the Hamiltonian case. So remember that in this case, which the cases that interest us, Hamiltonian means gamma equals to 0 and y equals to 0 also because of that observation I made back there. So we linearize the system around the equilibrium, and the system linearized is given by this matrix. And so we have the characteristic polynomial of this matrix is a cubic polynomial. And here we have already made the substitution. We called the eigenvalue lambda, and we call S the square of lambda. So we have this polynomial of degree 3, which we have to analyze the roots. Okay, the coefficients here in the polynomial B4, B2, and B0 are expressions given in terms of the angular velocity and the derivatives of V, given by this expression 36. And we make use of the Sturm theorem to analyze the all possibilities of real roots for that equation. And we have this theorem 1, meaning that in the Hamiltonian case, that's the case where the normal vector of the sail is parallel to the direction of the vector, the position vector of the sail in relation to the sun. Equilibria in the plane given by y equals to 0 are linearly unstable, except the equilibrium given by the point x0, 0, 0, which is stable, linear stable. Okay, so once we can't find stability in the Hamiltonian case, we move on finally to the non-Hamiltonian case. Again, we linearize the non-Hamiltonian case around the equilibrium. And I have this matrix A here, a little bit more complicated. Oh, okay. Just a word of caution. These A's that appear here are the components of the acceleration due to the solar pressure. Okay. All right. I have to make this comment because I use the same letters here in the characteristic polynomial. I use the letters A. And I just saw it now when I was preparing this presentation because the referees that judged the paper, they didn't comment on this. Otherwise, I would have changed the notation. Anyway, we have the characteristic polynomial given by this polynomial of degree 6. Okay, in which you have the expressions for each of the coefficients. A0 is equal to 1, A1 is equal to 0, and the others are a little bit more complicated. They are given here, A2, A3, A4, A5, and A6. Okay, we observe that using the root width criterion, because we have A1 equals to 0, that implies that at least one of the eigenvalues has a non-negative real part. So there's no possibility of a symptotic stability in this case. Okay? Okay, so we now search for a criteria for Lyapunov stability with the eigenvalues being pure imaginary. So what we do is we substitute S by IS into the polynomial. I means the square root of -1. And we get this expression here, and we break down our polynomial of degree 6 in two parts, the real and the imaginary part. And in order to have a pure imaginary eigenvalue, we must have S satisfying both equations 48 and 49. All right? The S's that satisfy both of these equations will be the solutions we are looking for. So you see here a necessary condition for the equilibrium, because P2 has an S over here, so 0 is a root of the polynomial P2. It must, in order to have coherence of the equilibriums, we must have S equal to 0, a 0 of the polynomial P1. So we must have this coefficient A6 must be 0 also. All right, so we consider two final cases. We consider the case in which the sail is on the ecliptic plane which means h equals to 0. And this implies we look for x is negative or 0. And this implies that delta is pi over 2, as we had seen earlier. Well, we made some calculations, and for this simpler case, we have some coefficients equals to 0. And the coefficients of our polynomial become, as given by equation 50, much simpler than before. A4 and A6 are a little bit more complicated, but remember, we have to demand that A6 is equal to 0. So when we ask for this condition, A6 equals to 0, A6 will be obviously equals to 0. And inside A4 here, there's an expression using part of A6. So A4 will be simplified a lot also. Okay, that's what I just said here. When A6 is equal to 0, this implies x equals to 0. Oh, I think this is not correct here. I think this must, let's see. But what it implies is that S0 equals to 0, and S2 and S3 given by plus or minus the square root of A5 and A3, which coincides to plus or minus the angular velocity, are roots of both the polynomial P2 and P1. Okay? So that both of these polynomials, they have the same root, exactly the same root, and there is no inconsistency between the equations. Okay, so now we analyze the condition for A6 to be equal to 0, and I computed this value. And we find that y bar must be given by this number, and P0 equals x equal to 0, y bar and 0, is a linear stable equilibrium of the Sun-Earth scale problem. Okay? Although it may be useful for theoretical reasons, this is not interesting in practice, because the value of y bar is much smaller than the radius of the Sun. So this equilibrium point would be inside the Sun and wouldn't be good for any practical mission. So I apologize, and I come back here, and I have to re-say what I just said, and this observation is correct. I just got confused when I saw this here. So the fact that A6 equal to 0 really implies, in this case, implies that x equals to 0, which features this P0 equilibrium point, which is 0, y bar 0. Okay. But for this point, is only one point, okay, we have linear stability. The second case we want to analyze is when y is equal to 0. So we are in the x-age plane. This implies that delta equals to 0. And we consider, without any loss of generality, that x is negative and age is positive. We compute the values for the coefficients of the polynomial, and they are given by this equation 55. Very simple equations. A4 and A6 are still not so simple, but again, we have to ask A6 to be 0. And when we do this, okay, we repeat the same procedure as before, and we get the polynomial of 6 degree, all right? And we substitute S by I S again, searching for pure imaginary solutions. And we break this polynomial again into polynomials. And what happens here is that the polynomials we had there before, P1 and P2, now in this specific case, A3 and A5 are equals to 0. And this implies that the second polynomial is null. Let me just come back here a few slides to show you what I'm talking about. I'm talking about these two polynomials. And so R5 and R3 are equals to 0 in that second case. So this polynomial is always 0. And we end up with only this polynomial P1 given by the equation 48, which I think I have changed the name and called the polynomial PA here. This PA is actually P1, all right? So we repeat the arguments that we've done before. We call zeta S to S squared, and you get a polynomial of degree 3, okay? And we must analyze when, now, because of this, we must analyze when this polynomial of degree 3 has 3 positive real roots, all right? Because when they have positive real roots, the S will be real numbers. We use the Sturm theorem to analyze the possibility when this possibility happens. And the Sturm theorem gives us these 5 conditions given by these 2 inequalities here, 2 inequalities in equation 2, and this only one inequality in equation 3. So we plot all these conditions together, and together with the condition, the additional condition, well, let me see here. Oh, okay. Here we don't have the additional condition of A6 equals to 0, right? Because we don't have the polynomial P2 is always null, is always any value of S or zeta is a solution of polynomial P2. So we have no need to demand that A6 is equal to 0. So when we use the Sturm theorem, we get these conditions, and these conditions in A6 is correct. For a minute, I thought it was wrong, but it's correct because of this argument I just said. And we plot this region. And in the next picture, but before I will read here the main conclusion of the work. Let's see, the figure 3 is this one. This represents the region in which all those conditions for the use of Sturm theorem are satisfied. So that's what's written here, right? In figure 3, we show the region for which all the 5 conditions are satisfied, and I ask X to be in this region, meaning that the X is not inside the sun. R, big R, so means S is the radius of the sun. So it's outside it's really behind the sun. And I put here another limitation for X, that is -1 astronomical unity, right? R, big R, so means E is the distance from the Earth to the sun. And also I asked H, consider H in this range of values. And so I can find the values for X's and H for which there are equilibria and they are linear stable. Even more, as I have freedom in choosing either X and H, with a little bit more of little bit of trigonometry, I can choose the value of age in such a way that it's high enough in order to permit to allow direct communication with Earth. Okay, and that's what I mean here. Also, this expression for age in function of axis is linear in axis and satisfy both these relations here. The values in the extremes are calculated here to show that the point given by P, oh, here is missing the y, right? Y is equal to 0. The point given by x, y equals to 0, and h of x given by this expression is inside the region, the blue region given by the figure 3 here. So, which means that, let me see if I put this as a, yes. So I have this result here. The family of equilibria given in the second case, given by a negative axis and any positive h, is inside the blue region of figure 3. And the expressions for gamma and beta as functions of these values can be chosen in order to futures equilibria that are linear stable. And further, if we choose x's satisfying this expression here, we can guarantee direct communication with Earth. Well, I thank the CNPq for the grants which made it possible to go to Rio Claro and work for a year with Professor Tadashi. Here I show some of the biography. If someone wants more details, I can give more details to anyone. Okay. And I want to wish happy birthday to Hildeberto. May God bless you, give you a long and a good health life, Hildeberto. Here's a photo. I searched last night, I searched for photos of the good old times with Hildeberto, but my photos are all dying out, the colors. So I only found some photos of a meeting in Alagoas, I think, Maceió, organized by Hildeberto. Here we see a dancer doll on his lap. Another picture here of Hildeberto working in a class. And the following picture is for everyone who thinks about messing around with Hildeberto. Don't do this, because Hildeberto was very mad bodyguards. And if you mess around with Hildeberto, they will shoot you. That's what I want to talk. Thank you for your attention.
Thank you, Marcelo. Okay, are there questions or comments?
Oh, I'd like to make one comment. Okay, so the reason that L1 and L2 are people send spacecraft to L1, L2 for Earth is because they are still equilibrium, but L3 is not equilibrium in solar system. So L3 in solar system, it's not a equilibrium point because the perturbation from other planets is much, much larger. For L1, L2, if you do a little calculation, L1, the distance to Earth is about 1.5 million kilometers. So the perturbation, the force on L1 and L2 basically is given by Earth. But L3, the distance to Earth is about, well, it's 2 AU, but its distance to Jupiter is only 6 AU, the maximum. So the force by other planets is very, very large. So therefore, all these, I mean, the equilibrium L3 that in the solar system, they're not equilibriums. So the force by cell is very, very tiny compared to other planets. So your analysis mathematically is correct, but it's not applicable to the solar system. I'm not sure if you understand what I said. Yeah. L1, L2 are equilibrium solutions in solar system, but L3 is not equilibrium for solar system.
I understand.
It's only strictly in three-body problem that's equilibrium. But L3, L1, L2, even in solar system, it's still equilibrium, close to equilibrium, because the error, the perturbation by other planets is very small. It's a magnitude of 10 to negative 2. But the L3, the perturbation is so huge, it's not possible to keep anything there.
Okay.
Okay, so that's my comment.
Thank you for the comment. Maybe you could introduce these perturbations and analyze it in a more realistic problem.
This is not part, because if you think about it, the distance L3 to Jupiter, the maximum is 5 AU.
Okay, I understand.
Okay, and the shortest time is only 4 AU, L4, L3. So if you take inverse squared, the maximum is 1/25. The force by Jupiter, it's 1/25 to 1/16. But the Jupiter has a mass about 1,000 times of Earth. So the Jupiter, the attraction is 1,000 times. If you divide by 25, or inverse squared, it's 36. It's huge.
Okay, I understand. Maybe you should consider only the theoretical result then.
This is a theoretical kind of a result, but not applicable to solar system.
Okay.
So the reason you see that people send spacecraft to L1, L2, these are still equilibrium solutions because the distance to Earth is about 1/100th of AU. It's 0.01 AU. So the distance is so small. If you take a inverse squared, that's about 1/10,000. Jupiter, the size is about 1,000. Therefore, the perturbation from Jupiter or from any other planet for L1 and L2 is very, very small. So therefore, they are still equilibriums. But L3 is totally different. So there's no way, I mean, it doesn't make any sense to send anything to L3.
I'm sad to hear that.
That's my remark from astronomy.
Okay, no, thank you. I didn't know that.
Okay. Yeah.
Okay, Jeff, thank you very much. Other questions or comments or? Okay, so let's thank Marcelo again for the talk. And I guess that's it for today, right, Annette?
Yes, I will stop to recording. So if you want to open your cameras to take a picture.
Yay!